The submitted article is titled Design of Transformerless DC Regulator with Reduced Redundant Power Processing for the Residential DC Microgrid. The authors are PhD Ivan Alfonso Reyes Portillo, Master in Engineering Saúl Rolando Méndez Elizondo, PhD Jorge Alberto Morales Saldaña, PhD Claudia Angélica Rivera Romero, PhD Dora Luz Castro López. In the pursuit of more sustainable future, DC microgrids offer an efficient solution by integrating renewable energy sources such as photovoltaic panels and wind turbines. By operating on direct current DC, these networks minimize conversion losses, optimizing efficiency and reducing costs for users. DC microgrids allow households not only to consume energy, but also to produce and store it, promoting energy autonomy. However, due to the intermittent nature of renewable energy sources, it is necessary to integrate backup energy systems, such as battery storage or grid interconnection. The submitted article proposes the integration of a quadratic buck converter with reduced power processing based on an LC filter scheme that eliminates pulsating current. The article presents the operating points, the voltage and current ripple values in their reactive elements, and the operating states of this topology. The reduction of power processing to improve efficiency is one of the key concepts proposed by partial power processing for high-gain converters. This structure introduces a buffer element that processes a portion of fraction of the power directly to the load from the second stage of the converter to the output. One of the advantages, analyzed through the area modeling as proposed in this article, is the ability to evaluate the directly processed power, which enhances the efficiency of these structures through a factor of K, examined in detail within this document. In addition to presenting the reduced redundant power processing analysis, the article also introduces average models and linear models, which are fundamental for designing control laws that ensure proper regulation of the interconnected DC bus to the DC microgrid. The operating points of the average models, as well as the system design, have been validated through calculated values that enable experimental testing on the system's interconnection. It is important to mention that the average values obtained at the operating points have been calculated, validating the initial equation proposed in this article. In addition to validating the average model, the linear model was verified through frequency response analysis, comparing the mathematical linear model obtained in this article with a switch model. This comparison allowed the validation of the proposed scheme using two different software programs, MATLAB and PowerSim. The poles and the zeros of the frequency response of the output voltage transfer function with respect to the duty cycle were also determined. It is important to note that this is a minimum phase system, where three right half-plane zeros are present. This system exhibits complex dynamics in terms of voltage regulation. This highlights the importance of the controller design, for which a Type 3 compensator based on controller was selected. Why was this compensator chosen? It was selected because it includes a pole at the origin which allows for low frequency disturbance rejection and better reference tracking. It is important to mention that only a voltage loop is used, as the system itself enables cost reduction by eliminating the need for current sensors, thus avoiding the implementation of a second current loop. While a dual loop approach could enhance the system dynamic performance, it would also represent a significant economic cost for this type of system. After completing the mathematical analysis and controller design, experimental tests were conducted where the system's waveforms were obtained at different operating points. This includes the transformation radio, buffer voltage, input and output currents, inductor currents, and the load variation. This allows us to observe the regulation capacity of the Type 3 compensator. We can observe load changes from 325 watts, the operating point, to 440 watts, the maximum demand point, which allows the platform to perform the test. It is also worth mentioning that for DC microgrids, disturbances traditionally occur at low frequencies due to the types of residential loads, which is why this type of controller was chosen. The article presents the proposal to integrate DC-DC converter based on R2P2 concept to DC microgrids, analyzing both the design methodology and the operating analysis of these methodologies. This leads to a mathematical analysis followed by a validation through numerical simulation. It is also important to mention that the article presents experimental tests, as well as the validation of those same analyses in comparison with the theoretical results obtained. An efficiency analysis of the entire system was conducted under open loop and closed loop conditions. The article concludes with final remarks where future work related to this document is also discussed. This concludes our presentation. For any question or comments, please feel free to send us an email. Thank you for all.